So hello everyone, my name is Fabio Diaz. I'm a postdoc researcher at the University of Helsinki, Finland. And this is the longer version of the talk on the water mass transformation of the Antarctic shelf. So basically, you know that the Southern Ocean has pretty large role in the climate system, basically because of the formation and subduction of Antarctic bottom water, which is one of the most dense water mass in the global ocean. And so this water mass sinks downslope around the Antarctic continent and fills very large part of the ocean abyss as part of the global regional overturn circulation. The formation of Antarctic bottom water is linked with the High Salinity Shelf Water formation, which occurs over Antarctic coastal polynyas, so where the wind pushes, the offshore winds push the sea ice offshore, and this creates this ice-free area, which has quite lots of exchange, especially heat loss to the atmosphere. But because it's a region of high sea ice production, it also has quite lots of salt rejection, and that creates this near freezing temperature and high salinity water mass. But the waters sitting at the Antarctic continental shelf are also important for global sea level. Basically, it's depend on the water that is filling the ice shelf cavities, which these floating ice shelves maintain the stability of the Antarctic marine ice sheet. Independent of the water that's sitting on under the cavity, it can cause basal melting, which ultimately produce the ice shelf water, which has even lower temperature than the surface freezing point because of the pressure effect that has quite low salinity. Now our goal here is actually to investigate the interaction of these water masses on the Antarctic shelf and make use of the water mass transformation framework. And our specific goals is to quantify the rates of water mass transformation over the Antarctic shelf and investigate the driving process. You also had a look on the sensitivity of this process to horizontal resolution, bathymetry, and tidal forcing. So we use this Circumpolar Antarctica regional model based on Ronne's. It is an ocean ice shelf model. It is configured with 3 different resolutions ranging from 10 to 2 kilometers and include tidal forcing, forces with equal boundary conditions, and air entering winds. But this model doesn't have a sea ice component. It actually is forced with surface heat and salt fluxes estimate from sea ice thickness based on satellite observations. There is this Tamura product, and that is actually a good strength of the model because it represents pretty well the locations and the flux associated with the coastal polynyas and therefore high salinity shelf water formation. So very briefly, the water mass transformation quantifies the rates of transformation towards heavier or lighter density classes. And here you use the heat and salt budget diagnostics based on the potential temperature and salinity conservation equations. And these equations basically have terms to quantify the local contribution, the temporal tendency in terms of temperature and salinity, and decompose this tendency into contribution from advective, diffusive, and surface flux processes. And then you combine the heat and salt budgets in via potential density equation, use the heat expansion and salinity contraction coefficients, and then you bin those diagnostics into different density classes. And then to obtain water mass transformation rates in Sverdrups, you integrate everything over the vertical over the meridional mixed layer depth and horizontally. So that this is more or less what to obtain is that you have the transformation rates in the y-axis. Positive values mean that the water are becoming heavier, and negative values mean that the waters are becoming lighter. And then in the x-axis, we have the the different density classes. So here we show the heat budget in the upper row and salt budget on the lower row, where the surface fluxes are representing the magenta line, And here you observe that the surface heat flux, it contributes to transformations toward denser waters, but is almost fully compensated by the opposite effect from advection and diffusion. So you don't have a very significant net water mass transformation due to the heat budget. But in contrast, for the salt budget has a quite large contribution. So basically the surface salt flux contribute to transform waters towards heavier densities of heavier density classes, and towards light densities at lighter density classes. And the advection and diffusion, they partially offset this effect from the surface salt flux. But one thing that we observe here is that the black line, the net water mass information due to the salt budget, is quite sensitive to the horizontal resolution. And to understand this difference, you break down the Antarctica water mass transformation into regional areas. So basically, you divide the continental shelf into the ice shelf cavity portion and the rest of the continental shelf. So it's the left and right columns on this figure here. And you also divide it in different sectors of the Antarctic domain. And what you found is that basically the buoyancy scan is occurring under the ice shelves, which is associated with the meltwater and production of ice shelf water, whereas the buoyancy loss occurs on the continental shelf part, and that's related with the salt input and the formation of high salinity shelf water. But one thing that you identify here is also that the main difference in terms of buoyancy scan under the ice shelf cavities is occurring at the Ronne-Filchner ice shelf. And that's where we're going to focus on the rest of our study. So first, we look at the water mass transformation maps under the Ronne-Filchner ice shelf. Basically, you integrate all the transformation rates with the range where you have the larger buoyancy scan in the 10 kilometers region. And what you found is that the surface salt flux has a pretty similar pattern across resolution, but where you see transformation towards lighter density classes near the ice shelf front and the grounding lines, which relates with basal melts, and you have the opposite transformation towards heavier densities in the central part of the ice shelf, which relates with refreezing regions. And this pattern is actually quite in a good agreement with the observational estimates that we have so far. But besides that importance of this difference in this quantitative difference in terms of the surface salt flux contribution, the advective process also has a pretty big role into the difference across resolution. So to investigate the mechanism of salt advection, look at the bottom temperature and surface salinity annual fields here. And you found that as you increase the resolution from 10 to either 4 or 2 kilometers, you actually enhance inflow of a relatively warm and salt water via the bottom layers at the Ronne Depression in the west part of the Ronne ice shelf. And this inflow is driven by an anticyclonic circulation, which sits just in front of the Ronne Depression and the continental shelf. And this circulation is also bottom intensified and quite dependent on the resolution. Gets more stronger as we increase the resolution. And then after this warm water penetrates the cavity, it's spread into two different branches, one eastward and one southward. And that's pretty much agrees with what you know about the sub-ice ice shelf cavity circulation from observations. And this warm water inflow then causes surface freshening pretty much in most parts of the cavity. But very important, there's two regions that the warm water doesn't penetrate, and these are the shallow banks between the Henry and Corf ice ridge in central part of the cavity, and in the west near the Fowler ice ridge. And these are exactly the regions where you observe refreezing and water mass transformation towards heavier densities in the water mass transformation maps that I showed before. So then you look at these two transects, one in the west and one in the central part of the Ronne ice shelf cavity. And what these are salinity cross sections. And then you see that the inflow of warm salt water follows pretty much a baroclinic circulation, where you have this salt water in the bottom, and the melting creates this freshwater plume on top. So pretty stratified profile. But there are regions where this water gets mixed vertically, especially near the ice shelf fronts, and also in the shallow region between the Enhi and Corf ridges in the central transect between 79.5 and 80 degrees south. And this, because these are region where you observe refreezing, it has quite high salinity in comparison with the other parts of the cavity. And then to understand a little bit more on what these regions means for actual water mass transformations, you pin the transformations this time into the temperature and salinity space, which is the figure in the right, and you use the central transect for that. And what you see is that at the 10 kilometers, you have much more water mass transformation towards lighter densities. So basically, high salinity shelf water being transformed into ice shelf water in the 10 kilometers experiment. And this decreased substantially, even being more towards positive water mass transformation rates in the 4 and 2 kilometers regions, which mean that the refreezing over that shallow bank impacts the transformation of ice shelf water. And so last thing, we investigate the sensitivity of this result to the tidal forcing and the bathymetry resolution by conducting and using the 4 kilometer version, a no tide experiment and an experiment with a 10 kilometer resolution bathymetry. Basically, the coarse bathymetry doesn't impact much on the water mass transformation rates under the Filchner ice shelf, but the exclusion of the tidal forcing decreases substantially the water mass transformation rates associated with the surface salt flux. It still has a semi-pattern of melting near the ground line and refreezing at the central part of the cavity, but they are much weaker than you observe when you include tides. And looking again at the bottom temperature and surface salinity anomalies, we found that the tidal forcing is actually essential to simulate that anticyclonic circulation, which brings warm water towards the Ronne ice shelf cavity. So when you deactivate the tides, we cease that circulation, and we have very strong negative temperature anomalies near the bottom in comparison with the original 4 kilometer experiment. So just to summarize, our results show that the Circumpolar Antarctica water mass transformation is pretty much dominated by the salt budget, with very little contribution from the heat budget. And the continental shelf process of high salinity shelf water formation, it is very much linked with the surface flux product that you use. So it shows this more sensitivity to resolution. But on the contrary, the process of the ice of cavities have a quite large impact from the resolution, and especially under the Filchner ice shelf, we found this mechanism of warm water inflow, which influenced the melting and refreezing rates, but also impacts the rates of water mass transformation. So we have, with less warm water inflow, we end up having more transformation towards light densities. And as we increase the resolution and increase the warm water inflow, the refreezings become quite important to transform waters towards heavier densities. So we have less buoyancy gain under the ice shelf cavity with increased resolution. And basically, this process of warm water flow is driven by that anticyclonic circulation, which is very much linked with the tidal forcing and is very sensitive to the model resolution.